Here's our last section of this unit. Covers what's called sigma notation. This is the Greek letter sigma. It's like a capital E with these little points on it. This is what's used as a shortcut notation to represent series. Usually we see it written like this. We'll have some letter here. Usually it equals 1. There's another number up here. I'll just make one up, say 50. And then here, there'll be a bunch of stuff. Usually an expression, something like, I don't know, 2i plus 12 or something like that. This does not mean square root of negative 1. This I is just a variable. Could be J, could be K, could be A, N, could be virtually any letter that we choose. Let's run through a few examples. First example. Sigma, I equals 1 to 5 of 2i plus 3. The sigma basically means add up a whole bunch of stuff. And the things we add, we get from here all the way up to here. So let's start plugging things in to generate some terms, and then this means add up all the terms. So we start by plugging this number in for I. You do that, we get 5. Then we plug in 2. We increase this by 1, plug in 2, that's the next number, 7. Then we plug in 3. Then we plug in 4. Then we plug in 5. And then we stop. Since this goes from 1 all the way up to 5, we plug in 1, 2, 3, 4, 5, then we stop. Sigma is the notation for add up all these terms. And then we add up all these terms, we should get 45. Add up the terms from 1 to 5 that you get from this formula. That is really all there is to doing a sigma notation problem. Let's take a look at another one. Here we have, instead of I, now we have A. We have A squared minus 2. A equals 3 to 7. You do not need to start at 1. You can start anywhere you choose. You can end anywhere you choose. You can end at infinity. You can end at a very large number. You can end at a very small number. The only real rule is you have to always go up by 1. So we will plug in 3, 4, 5, 6, quit when we plug in 7. We plug in 3. 3 squared minus 2, 7. We plug in 4, 14. Plug in 5 to get 23. Plug in 6, get 34. And then we plug in 7, get 47. Add all those terms up. And I'll put my famous U finish here because you can add those up on your own. Plug in 3, 4, all the way up through 7. Sigma says add these terms up, and we'll get that number. We can have a series that looks like this. Add up the numbers from 1 to 4. Let's start plugging things in and see what happens. Plug in 1. Here I get negative 1. Here I get 2. Negative 1 times 2. Plug in 2. And we see immediately we will get 0. Plug in 3. We get 1 times 4. Plug in 4. and we get 2 times 5. Add these terms up, 12. So when we plug in values for the variable, we can end up with negative numbers. We can end up with 0. We will just never see negative numbers here or here. We may see 0 here. Think of that as a t sub 0 term. It's rare, but you could see that. We will never see negatives here. When you get into more advanced applications, you might see some negatives. Those are used for a little more specific situations. Last example. N equals 1 to 1,000. 1 to 1,000. 3n plus 4. Now, there's no way we are going to plug in every single number from 1 to 1,000. This should tell us that there's some kind of pattern that's going to emerge, and once we find the pattern, we'll be able to do this a little easier. Plug in 1. We'll get 7. Plug in 2. We get 10. Plug in 3. 13. Plug in 4. We get 16. And hopefully now you see a pattern. These are all going up by 3. This whole series is arithmetic. And if you remember how to sum an arithmetic series, we have the number of terms divided by 2. We need the first term. We need the last term. In this example, here's our first term. Here's the number of terms. When we start at 1 and end at 1,000, we've summed 1,000 terms. First term was 7. We need this last term. Whoops. We need this last term. How do we get the last term? Well, here's the last number. Plug it into n. 3004. And since I don't have my calculator on me, I'm not sure exactly what this will come out to. It's a big number. It's over 1 million. I'm confident that you can calculate that on your own. Once you have that value, that is the sum of this entire series. Large series like these, you can often shortcut by recognizing what type of series it is and using the appropriate formula. If we were to sum this to infinity, we would need to have a geometric series here, and we would find that value of r by looking at the terms, first few terms, find our value of r, and then use the geometric series formula. Series have a lot of applications that are beyond this course. You will encounter them if you take Calc 2. You will encounter a lot of them if you ever take a stats course someday. We're just going to focus on the basics of how do you interpret the notation and then how do you calculate the series. As always, make sure you do your completion quiz at the end of this lesson, and that is all for today.